Okay, this is module 9B, looking at the Brayton cycle, ideal versus real Brayton cycle, and an introduction to the Rankin cycle. Here's a layout of the Brayton cycle. Here we have work coming in, added to the compressor. This is a steady flow compressor where air is drawn from the surroundings, goes through the compressor, gets compressed to a high pressure and also a relatively high temperature, runs into a combustion chamber where its heat is added. Usually that is some sort of fuel, either natural gas. Brayton cycles are used for jet engines, so that could be jet fuel added in the combustion chamber. It then goes to a turbine, and the turbine expands the gas where it was at a very high pressure and very high temperature, and then it expands and back out to the atmosphere. Technically, you could have a cooling, a fourth step, a fourth unit where it's cooled and heat is removed to the atmosphere. But in practicality, air is just rejected to the atmosphere and fresh air is brought back in with its fresh oxygen that can be used for the combustion up here in the combustion chamber. That's the Brayton cycle. For the ideal Brayton cycle, steps 1 to 2, we consider that to be an isentropic compression. Steps 2 to 3, isobaric heat addition, meaning constant pressure. 3 to 4, again, you have that ideal workout, ideal expansion or isentropic expansion, an ideal turbine, if you will. And 4 to 1, we have an isobaric heat rejection. Again, you're just rejecting heat to the atmosphere as the air cools down after leaving the process. Here it is on a PV diagram. Basically, you start with state 1 with a low volume and a low pressure, and then you raise that. You raise the pressure up as you compress it, and the volume's getting lower. Here you're adding heat at constant pressure in your combustion chamber, so the volume goes up, the temperature goes up, and since the pressure is held constant, the volume also must go up. Remember, PV equals nRT. Now as you go through the turbine, you're dropping pressure and your volume's increasing, so you got a lot of work coming out there, and you wind up at state 4 with fairly hot gas, not as hot, but a low pressure back down at atmospheric pressure. Again, this is brought back into the engine. Usually it's fresh air that's brought back in. For a real Brayton engine, we need to use adiabatic efficiencies for our compressor and our turbine to get the, quote, real work that happens. What I usually do is set up a chart tracking knowing the inlet temperature and knowing the inlet pressure, typically 1 atmosphere. Maybe a slight vacuum as it's drawn into the turbine. And then we have an enthalpy. This was taken from the ideal gas tables. For ideal compressor, S2 equals S1. I like to do this with assuming constant values of CP, just to illustrate the process. Obviously, you need to have doing this professionally, you'd want to make sure you took into account the changes in CP, and there are various ways to do that. But assuming constant CP, then we can calculate T2 for the turbine, for the compressor, leaving the compressor. T2 equals T1 times the ratio of P2 over P1 to the K minus 1 over K. Recall that from your constant entropy ideal gas process. And find out that T2 ideal would be equal to 589. Now taking enthalpy with a reference state of 0 Kelvin, then the CP times the temperature would be equal to the enthalpy. Let's see, that would be equal to H minus H ref, and taking H ref to be 0 at T ref equal to 0 would give it to us that way. Reference state 0 Kelvin. All right, suppose T2 is measured. All right, we found that T2 earlier we said was 589, but suppose we measured it and found out it was 670. What's going on there? Well, there was friction, and the friction wound up getting into the gas and heating the gas, leaving the compressor. Talking about a compressor here. So what is the efficiency of the compressor? You can do this by calculating H2 real from the temperature. Use Cp times T, again with the reference state of 0. And the real work would be 366. So having measured the outlet temperature, I could calculate what the efficiency was of the compressor, because I knew the ideal work, the ideal delta H, 285. The real delta H is 366. So for a compressor, it's the work that you might have done divided by the work that you actually had to do. So this is, let me write it out, equals work ideal over work real, and that gets you your efficiency of 78% for your compressor. The ideal turbine, S4 ideal equals S3. Similar calculations there, and we wind up with our ideal temperature and ideal enthalpy leaving the turbine. So suppose we found T4 to be 800. Let me go back one. T4 was 694. And usually in the non-ideal it's hotter, and in this case that's true. The heat of friction as it went through the turbine wound up in the exhaust gas, and instead of dropping all the way to 690 or something like that, we wound up dropping our temperature only to 680. I'm sorry, to 800, and therefore we get less work out of the turbine. Well, that's a mess. The ideal work turns out to be 649. This is apparently the actual work, 543, so it's easy again to calculate the efficiency. In a turbine, it's the work that you get, which is usually always less than the ideal work actual divided by work ideal, and that comes out to 84%. So if we summarize this and put our enthalpies up here in a chart, then we can start to do our energy balances to find the thermal efficiency of the overall process. Now the thermal efficiency of the process is different than the isentropic efficiency. Isentropic efficiency deals with a particular piece of equipment. Thermal efficiency is the work that you get divided by the heat that you put in for the overall process, the net work that you get. So thermal efficiency here, put in some, we have work out, doing our energy balances about the compressor and about the turbine. The net work is the difference of those. The heat in, doing the energy balance from the combustion chamber, we find that we had to put in 674 units of heat. And so our thermal efficiency is 26%. The work net over Qn, or 26% for that cycle. If the turbine and the compressor were ideal, then we would have gotten, you plug in the energy balance on the combustion chamber and find out that we put in 755, but we also got 649 units of work out of the turbine and 285 out of the compressor, into the compressor, out of the turbine. The difference between those divided by the heat in is 48%. So these, the Brayton cycle is very sensitive, I should say, to the inefficiencies that you might have in the turbine and the compressor, because those work against you. So we got quite a bit more, 48% versus 26%, if we did have an ideal turbine and compressor. Now I like to look at the overall process. And suppose we had an idealized process, the best process we could ever come up with. We've looked at the real Brayton engine. We've looked at the Brayton engine with an ideal turbine and an ideal compressor. Now let's suppose we had some ideal heat engine overall operating between these two temperatures, 1340 and 305. Using the Carnot efficiency, which is the best we could do, 1 minus TL over TH, we had 77%. So real, 26%. Ideal turbine and ideal compressor, 48%. Ideal, complete, process anything you can dream up, 77%. So this is where our work as engineers comes. How do we get toward that 77%? How do we design an engine that can do that? And there is no such engine, but that's what we're trying to accomplish. In summary, we have this overall best we can do, 77%, 48% for an ideal turbine compressor with a Brayton engine, and finally a Brayton engine with a real turbine, real compressor, 76%, given those temperatures that we're working with. Now let's look quickly at the Rankin cycle. I just want to introduce it here. In a Rankin cycle, we have steam. Steam is the working fluid, or water, let's say, is the working fluid. And we'll take our heat in and we'll boil the water. But to have the motive force to run the turbine, we need to have a high pressure. So first we have to pump the water from a liquid to get a high pressure liquid going into the boiler in the first place. Technically we have a superheater here too, so this is a boiler and a superheater that will really use some of that Q to superheat the steam too before we put it into the turbine. So we'll have the liquid pumped up to that high pressure so that when you do turn it into a vapor, it's got a mechanical potential pressure. When you boil it and then superheat it, it'll have a high temperature and pressure. Temperature and pressure will both be high. We'll put it in the turbine and take that mechanical potential and drive the turbine, and we'll use the thermal potential to get the energy out of the turbine, and both those together give us this work power out. Now the difference between one of the main differences between a Rankin cycle and a Brayton cycle is this is very large, because we're expanding a gas. This is very small, because we're compressing a liquid, and it takes very little power to compress a liquid, because you got this V delta P thing coming on, and the V is very small for a liquid. So this pump work is going to be relatively small compared to this very large turbine output. We use cooling water to remove the heat in the cycle. Now in the Rankin cycle we do reuse the working fluid, mainly because these liquids that we use are usually treated with anti-corrosive agents and different things that make running through this heat exchanger. You want to make sure you have low corrosion in your heat exchangers, and so you'll treat your water and make it that's kind of expensive, so you want to reuse that water. Here's a TS diagram for an ideal Rankin cycle. We go through our pump at constant entropy from state 1 to state 2. Then we heat the fluid till it gets to its boiling point at that new high pressure. Then we boil it at the high temperature pressure and the high saturation temperature corresponding to that pressure. Tsat, let's call it. Then we superheat it along this constant pressure line, approximately constant pressure through our heat exchangers. And then we drop it through the turbine down into the saturated region, but just barely. You don't want to go too far into this saturated region, because if you get too much moisture, see this is right here, quality of 1, right here, quality of maybe 95% or so. If you get more than about 5% moisture in this turbine, you can damage the blades of the turbine because the little droplets are pinging against there. Think of it that way. And then we'll condense it back down, and at constant pressure, as we remove heat, the entropy drops, and we start all over again with a liquid. In truth, you won't use a saturated liquid. We'll use a, we'll use a subcooled liquid, so you may come down here to, to a lower temperature and subcool before you actually go into your pump. Truth is, if you go into a pump with a, here's a pump, if you go into a pump with a saturated liquid, the pressure drops as it goes into the pump, and then you're vaporizing your liquid, and then you have bubbles. And the bubbles do a similar thing to the pump impeller that the little drops of liquid do to a turbine impeller. They damage the blades or damage the equipment. Here's a real Rankin cycle. In a real Rankin cycle, what happens is in the pump, the entropy increases a little bit, and also in the turbine, the entropy increases as you go through the turbine, rather than this straight line down that we had for the ideal turbine. So you use the isentropic efficiency to calculate the real work, just as we did earlier with the Brayton cycle. So they're not isentropic. You have to use adiabatic efficiencies or isentropic efficiencies to calculate those works. Here's an example. A simple Rankin cycle produces 150 megawatts of power. You're given the low pressure and the high pressure. You're given the max steam temperature, which would be entering your turbine, and you're told that cooling water is available. And the cooling water, due to environmental regulations, is often limited to a certain rise in temperature. So we bring in cooling water at 25 degrees, and our cooling water is heated to 35 degrees at the most in your condenser. Let's suppose turbine and pump efficiencies are 85 and 75%. And let's suppose liquid enters the pump as a saturated liquid. I want you to characterize this process completely. We'll save that for homework. Brayton cycle, you have a turbine and a compressor, constant pressure combustion chamber, and with ideal versus real, we looked at the real turbine and the ideal turbine and compared those, and compressor. And we compared that to an ideal cycle overall, the Carnot cycle. Introduce the Rankin cycle as a pump, a boiler, and a superheater. This is the minimum for a Rankin cycle. These things have all kind of improvements, just as an automobile engine would. Have a turbine and a condenser. And for homework, what I want you to do is rework the Brayton cycle problem we did, and assume that the compressor and turbine efficiencies are 90%, and see what you get there. And work problems 83 through 87. And 91, 95, and 100, and assume constant CP when you're solving those problems. That's it.